do I show that like what I got is the integral? Like, you know how like we go through and we solve and then we take the integral of it?
Yeah.
Like, I don't want to, like, do I write like f of x? Do I write like...
No, you don't have to, because it's just kind of saying take the integral of this, and so you could just use an equal sign. Here, I'll show you what I mean.
Yeah.
So I'm assuming you did e to the x for
Yeah.
u. Anyway, so that we can cancel that e to the x. What's the integral of sine of u?
Negative cosine u.
So here's what I was saying a second ago. Like, technically, if we had room, we could go this way, right, and just make sure that we say things that are equal. So you can just say, well, it's still equal to that, and then once we've done the integral, now we can say cosine of e to the x plus c. Do you remember your plus c?
Yeah. I've been getting calculus meetings on my feed now. There's this one, and it was like something about like forgetting C, and a song that says, "Oh, don't forget this." And I laughed at it. And I was like, "Oh, geez, I'm such a nerd." Like laughing at calculus meetings.
That's funny. That's a good place to be.
Or like chemistry memes too. I find like a lot of chemistry memes. I'm like, oh, geez, am I really laughing at these?
Are they pretty funny?
They are funny though because they're so relatable.
Yeah.
It's like when you tell your lab partner that you somehow got like 420% error. And you laugh.
I forgot about that. You do have to calculate your error. Yep.
I was like, that's funny because it's definitely happened before.
Yeah. I know, makes you realize how sensitive some reactions are. You know?
Yeah. And it's like you did all this and you're like 90%.
Yeah.
90% yield or whatever.
Yeah. Did you do any that had the strategies that we talked about at the bottom? Let me get to it. So, where we had to solve for x, or I guess we didn't get to that one. Never mind. We should do that right now. Anyway, did you feel like you needed those on the ones you did?
I think number 3, I remember, was one of the trig ones. This was 1 plus x squared.
This one?
Yeah.
Oh, I see what you're saying. Yeah. So let's go talk about how to do that. Well, what does this one kind of look like?
The sine, inverse sine.
Yeah. I think I'm going to just grab a snip of it and move it down. Just get some more room. Did I paste it? Where did it go? There it is. Alright, so yeah, so it does look like we could make it as inverse, but we'll still need to do a u. So what do you think we should do?
The forward.
So it feels like it should be, right?
Yeah.
You said like 4x squared. So, but if you think of it, it would be 1 minus u then,
Also
right?
would be
Which isn't the inverse.
4x. Because then you have 1 minus u squared.
Except 4 wouldn't be part of that. So you're
2x.
close.
It would be 2x.
There you go. Yeah. Good job for thinking it through. Okay. Anyway, then what?
And then we can take the integral and we would have inverse sine.
Yeah. Which we could just substitute in 2x. And what are we not forgetting?
Let's see.
And we don't, I mean, it's a good strategy, but, you know, we only wrote down 2 of these. Inverse sine and inverse secant. So, you know, it's probably going to be this one if you're using it. I mean, not that this couldn't come up, but I think that would be a little more obvious too.
Yeah.
All right, these next ones are definite integrals, and it's kind of an interesting switch, kind of interesting process, I should say. Still recognizing that we have like looks like a product rule plus a chain rule, so use substitution. What would you pick for you?
Probably, t cubed plus 1.
Good, yeah. All right, but before we go back to the main integral, first of all, we see that this t squared's canceling, right? We're good on all that. So anyway, we can't just plug this back in and integrate with u. Like, think about what we'll eventually have is this square root of u, right?
Yeah.
Well, because we've changed what u is, or what's under that radical, by substituting, we have to change our limits on the integration.
Yeah.
So we can't just use 0 and 2. But what's nice is we can just plug 0 and 2 into u, and that will change them the way we need. So, like, I don't know how you want to notate it, but it would be like u of 0, essentially, right? So 0 cubed plus 1 equals 1. And then u of 2, it gives us 9. So we can, when we go to rewrite our integral, we'll change our limits to that instead. I still think it's good to write out everything.
Yeah.
And I think I'll write it as u to the 1/2 for now. So kind of cool, right?
Yeah.
Like that it doesn't have to, it's not really too big of a deal to switch it and be able to use this. So remember the notation. So what's the integral going to be of this?
Like we can put in.
Yeah, like, well, I'll just write it in 2 pieces, but that's what I meant.
Okay.
3/2 over 3/2. Do we have to write plus c? No. So we'll just write 1 to 9. And then what is this? 2. So this is 1/3, right? 1/2 times 3.
Yeah.
Or divided by 3/2. And then we get t cubed plus 1 to the 3/2 evaluated from 1 to 9. And we can actually take this all the way to an answer. like a single. So let's go ahead and do that. It's, for me, it's going to be squishy. Do you remember how?
Yeah, it's F of B, big F, B minus big F, right? So like plug in 9 minus plug in 1.
Shoot. Hold on. I'm making it too hard. Here's how. Sorry about that. Because we adjusted our limits on the integration, we don't actually have to plug this back in there. We can just use u, which is so much nicer, right?
Mm-hmm.
So just plug 1 and 9 in for u. And it's because we adjusted the limits that allows us to do that. That was the whole point of doing it that way. So it'll be just 1/3 and then 9 to the 3/2 minus 1/3 1 to the 3/2. And again, we can just put our equals out front. So 9 to the 3/2 is 27. Divided by 3 is 9. Minus 1/3. So 8 2/3.
Wouldn't that answer be in terms of u though? Like if we're thinking units, 8 2/3 u.
Well, but u is in terms of t.
Right. But I'm just like thinking like u's and t's like aren't the same size.
Units wise.
Yeah.
Yeah, that's a good thought. Let's think about that. Technically, it is in this case, right? Like, whatever t is, 1 would have to have the same units. So, u would just, it's not like we're doing,
Yeah.
like,
So
let's
it's
say
like
it's
in
feet.
the same units, but
Yeah. Like if it was feet, it would be feet cubed. This would have to be feet cubed, otherwise it would never add to it anyway. So then u would be feet cubed. So it should be okay. Yeah. Good thought though. Yeah, so this gives us a chance to work around having to plug that back in, which is way nicer. Okay, how about this next one?
we sign it back. Is that what we think? So maybe they can cosine. We cancel cosine.
Okay. Sine of pi over 2. Good. Alright, so our new limits are 0 to 1. Good so far? So kind of the same thing we just did, huh? See what I'm saying?
Yeah.
So this should be 3t squared. So let me go fix that real quick. Okay, so that's going to change this.
And also the other one there.
Oh, thanks. Yep. Alright, sorry video people. But I caught that was wrong. So, let's see, root, this is 27, and then divided by 9 is 3, so this is 6, minus 2/9. 54/9 minus 2/9 is 52/9, I think. So, alright, sorry about that. Anyway, kind of a cool option for doing definite integrals, and we don't have to go plug back in something that makes it more messy and hard. So, let's look at number 3. Now that we've talked through a couple of strategies, what are you thinking in that case?
You can use cosine so that we get 1 plus x squared at the bottom, which is inverse t.
Okay, yeah, I agree. Good job. Okay.
I don't think it's negatives.
Yeah, because derivative of cosine.
Oh, yeah, cosine integral.
I know, it's easy to get those backwards. Otherwise good? Let's look at number 4. Maybe it's too similar to the one we did a bit ago. But
yeah.
So skip it or do it?
I mean,
it's kind of the same, huh?
it's kind of the same. I know how to do it.
What would we plug in for
It would be 3x.
3x? Yeah. We don't have to do the whole thing. How about 6? Does it look any worse?
We could probably do cosine, and then so we would take the derivative of the sine, tangent sine of the cosine. Right?
I think it's easier than that. Well, how could we rewrite tangent?
Sine of the cosine. All times cosine of the cosine cancel.
Yeah. That's nice, right? But it's so easy to
I
not see.
immediately went to like, oh, I gotta find a u.
Yeah. Well, so you said make u be what?
Cosine of x, and then you would have dx is equal to the du over negative sine of x, and then we would cancel the sines from the tangents. You have 1 over cosine du. And that'll be using the growth of. I think we have 1 over.
I don't think we have a 1 over cosine. We'd probably have to do another substitution maybe and do 1 over u and then do natural log. I think.
Yeah.
And then it must simplify down to this in the end. You want to try it? Or not? Like a thought exercise?
So u is cosine of x.
Yeah, see, I don't think we have something over cosine.
I kept thinking like 1 over cosine was inverse cosine.
Oh, yeah. It's not though. That would be, what would that be, secant? 1 over cosine is secant. So if we did that, this would be u secant x du. If we chose, but then we would introduce another one, like another substitution, which wouldn't cancel our u, because there's no way to, secant derivative would cancel just a plain u. So yeah, I don't think this is very, well, we're not to the point of doing this one, at least. Because if we did u, like if, let's say we did, what did you decide you like w? Didn't you decide that the other day?
I'm doing b.
We did v, then it would be natural log, but it wouldn't cancel this thing.
Right, we would still have u.
So it would be u over v, which are different variables. Yeah. We haven't learned a strategy for that. There's something called integration by parts that it's a BC topic. I think it's in this packet. I think it's section 10 or 11. No, it's not 10. It's either 11 or 12. But anyway.
Yeah.
I thought about maybe doing it. Yeah, it's 11. Maybe doing it just to have it as a tool, even though we don't have to use it, but we'll have to think. We might come back and do it later, just to see if we have time. But this is a good thought. I'm just going to say not yet, or something. Okay, how about the next page? See if they just do the u substitutions jump out at you, like what you should do.
For 7. Probably tangent of x, because of the derivative of that. Is it not secant squared?
It is, yep. So it would cancel secant squared, and then we would end up differentiating or integrating that. Yep. How about 8?
Probably. Would it be? Well, because the square root of 1 minus x squared, so, because that would be the inverse sign. We just need 1 on the top. Be 2 cancel x dx. Oh, but is that dx the same x dx that goes on the outside?
Yeah. Just in a different spot.
So,
sorry.
Right. I'm just doing that right again.
would it be, the only one I'm thinking is x squared, and then when we take the derivative, we just have x, which would cancel the x on the top.
Okay. I think,
But then we get rid of the x squared on the bottom, which means,
well, if, right, and then it's no longer the
it's
inverse.
not the inverse sign.
So what if we did 1 minus x squared as u?
Oh, and instead of just doing sine, we did the natural log, or power.
Power, because it's square rooted. Yeah, and then we'd end up with a fraction, but at least the x would cancel. Should we do that one?
Yeah.
In rewriting all this, I forgot my negative sign, so let me, I think I'll just write it to the right, so it's gonna be a little bigger. There we go.
Yeah, I keep doing that.
What
When I
happened?
take the integral,
Uh-huh.
I wrote 1/2 u to the 1/2, but it should be 2 u 1/2 because we divide by 1/2. I multiply.
Oh, yes, I see what you're saying. Yep. So negative 1/2 divided by 1/2. Good. But otherwise, everything is good?
Yeah.
Okay, cool. Did you try it?
No, I'm just looking it over right now.
Okay. Well, we finished the notes while you're not here, but that one used just the stuff from yesterday.
But you substitution.
Yeah. How about number 9? What do you think would be a good U sub in there?
An actual one.
Let's do this one.
Yeah.
Okay. I'll wait for you a little bit.
Is it natural water next?
Oh, there you go for you.
Yeah, I got it.
Wait, the 1/6?
Yeah.
Oh, it's 'cause it's.
This one looks kind of ugly, but or would you use substitute there?
X plus 5. Because we have 2u. 2u times u x.
So if you think ahead with what the derivative would look like, I wouldn't pick x plus 5.
Oh, x squared plus 5x.
Yeah, because why?
Because the derivative is going to be 2x plus 5.
Yep. Yep, and then it cancels that, and we're just integrating u to the 7th, which would be awesome. Much better. How about 12? Actually, let's do this one. Or not do, but just mention it. What's a good strategy for 10?
U would be 5x. So we have 1 over u squared plus 1. And that would be the inverse tangent.
Awesome. Cool. And then it's just the inverse tangent. Yeah. Once you see them, they can go kind of fast.
Yeah.
But I feel like mixed in with a bunch of other kinds, it could be tough sometimes. Anyway, how about 12? That one's probably a good one to do.
We could probably
Let's
eat
do
it.
the whole thing. Just because it reviews something we haven't done in a day or two. So what'd you pick for you?
I said 4 minus u.
Good. Negative e to the x, yeah. Alright, we haven't seen this in a couple days. What's the, how do we integrate 1 over something?
Is that natural log absolute value?
Good, yeah. Cool. Alright, so Dylan, while you were gone, we talked about we did two things. We finished just use substitution on indefinite integrals, but then we talked about definite integrals and how we have to do a limit change, like a boundary. Well, if we do, then we can just do our integration on u and we don't have to plug it back in, which is cool. So which one of these three do you want to do? Let's pick one of the, either 14 or 15. Want to do 14?
Sure.
Okay. Do you want to do it together or do you want to try it?
Can be together.
Same? Okay. So what do you want to pick for u? Remember, whatever we pick has to have the dx equals du over whatever that ends up being has to cancel stuff to make this simpler. So if we pick this whole thing, we would get 18t, and now we have an 18t in the denominator along with our u. So it didn't get any better.
If we do u is 3t, then we get 1 plus u squared. That's inverse tangent.
Yeah, so this is one of the strategies we talked about also. If you look at a structure like this and it looks like it could be one of the inverse functions, like we see that it looks like 1 over 1 plus x squared, which is the tangent, then if you pick u in such a way that it makes it follow that, it's doable. But because this is a definite integral, what we're going to do is change our limits. Limit, change, limit shift. So we're going to evaluate u. What we defined as u, we're going to evaluate at these two limits on the integration to get the new limits. So u of 1/3 is just 1, because it's 3 times 1/3, right? And then u of negative 1/3 is negative 1. So negative 1/3 times 3 is negative 1. Make sense?
Yeah.
And what's nice about that, well, you'll see it better here in a second, but so our integral now becomes negative 1 to 1 instead of negative 1/3.
Oh, yeah.
Okay? And this is 1 over 1 plus u squared. And I can't forget this 3. So times du over 3, so we'll have a 1/3 out front.
Wait, but changing like the, I guess like the restriction or whatever, isn't that gonna change our actual value? Oh wait, no. Because you make it in terms of that.
Well, that's what we're about to do right now. So this is now 1. Do you see how this is the derivative of the inverse tangent? So going backwards, it's the inverse tangent, right?
Oh.
Of u evaluated from negative 1 to 1. And so this is what I was saying. We don't have to
Oh, yeah, okay.
resubstitute 3t in here. We can just leave u and do the 1 and the negative 1 on it, which is way nicer, right?
Yeah.
So this is 1/3 inverse tangent of 1 minus 1/3 inverse tangent of negative 1. That is not right, that first one right. Inverse tangent of 1. Okay. What's the inverse tangent of 1?
What is it there? Isn't it like all of the...
It would
like
be
it's gonna be pi over 4
and 5 pi over 4.
And then also...
Just those two. Well, unless we keep going.
Yeah.
Yeah. So we didn't have a restriction
It
on
doesn't
this.
have it. Yeah, so we don't know.
So what'd you say?
So like we don't know.
Yeah, true. So let's say it's pi over 4. So one would be pi over 12 minus, and then negative 1 would be 3 pi over 4. So what would that be?
1/3
Minus
times 3 pi.
negative. No,
Minus-
it's positive.
minus 1/4 or pi over 4.
Yeah, pi over 4. So let me write it. What did we say on this one? Pi over 12 minus pi over 4. Okay.
I think it's negative 5/6.
Yeah, this would be 3 pi. So pi minus 3 pi over 12 is negative 2 pi over 12. So negative pi over 6. Cool, that was a good one. So big idea, Dylan, is if you have a definite integral and you're using U substitution, plug the given limits into your U and use those. You don't have to plug in whatever you defined as U, which is nice. Like, let me show you when we did. Is it here? Yeah. For the example, I don't know if you want to see the whole thing, but we plugged in U as t cubed plus 1, which canceled the 2 or the t squared, etc. Okay, then we came down, we were integrating this, which is 2/9 u to the 3/2, once we got there. Okay, and then I made the mistake initially of plugging t cubed back in here. And so then I was plugging 9 cubed square rooted, and it was just a mess. Or 9 plus, what was it? Yeah, it was 9 cubed plus 1. Anyway, it was like not even correct, but also was way harder. So anyway, we didn't have to. We could just plug 9 in for U. 9 square rooted cubed was 27, and it was pretty easy from there. So. Yeah, and then same like this one. U we defined as sine x, and this was our integrated function. So it was pretty easy just to plug 1 in for U instead of dealing with like sine to the 3/2 and stuff. Cool. All right, let's look at some more.
I feel like all teachers say cool.
Oh, well, I should stop then.
No, you shouldn't. I think it's cool when teachers say that. Because it's like, some teachers are lame. But it's like with cool teachers, they're always like, yeah, that's cool. Like, I don't know how to explain it. Because I noticed it with, Mr. I think it's Mr. Ballard. He's like the National Honor Society guy.
Oh, yeah.
So like I was there in the meeting and he kept saying cool, but it's like cool because I don't know. I just,
Yeah.
it's like little things.
Low-key.
Mr. Ballard was cool. I had him for